this n number 4, but I trust that you're not gonna just look at the solutions without trying to learn the point of these exercises. So, games, these two ones. Oh. Maybe it's this one. No. This one. Okay. All right. So, essentially, in this exercise, the point was to take the games that we had been playing so far with deterministic equations and to try to imagine that our rates are actually the rates of a stochastic Poisson process, okay? So, let's say that we have our payoff matrix, Hawk those. We have our G minus C over 2, our G0 G over 2, okay? This is, again, the material of last week's game theory course. Now, each of these entries, PHH is the payoff that a hawk gains against playing a hawk. PHD is the payoff that a hawk gains against a dove. And then you have PDA, PDH, and PDD, okay? This is the structure of this matrix. So, if you have a mixed population where X is the fraction of hawks, and you sample from this population, the probability of sampling a hawk is equal to X, and the probability of sampling a dove is equal to 1 minus X, okay? Clear so far? Okay. So this means that given that you sample a hawk against another hawk, so you're gonna have, this is a two-player game, okay, remember, 2 players. So you need, for each interaction to happen, you need to sample 2 players, okay? So you're gonna have to sample the focal player of this game, and the opponent, okay? So when you draw 2 hawks, so a hawk against another hawk, that has probability X squared, and in that case, you're gonna have a rate of PHH of some event happening, okay? Now, these payoffs can either be positive or negative, depending on the values of the parameters. In fact, in this specific game, the only one that can be negative is this one. But you know, you have other more general situations in which any of them could be negative. Okay. So what you need to do, this is an algorithm where you don't have an integrator that advances time for itself. So essentially what you're going to do is that you're going to implement an equivalent of the Euler method for stochastic processes, okay? This is essentially what this algorithm does at this point. So this means that you're going to cycle over time, you're going to loop over time, and you're going to have to advance the time yourselves. You don't have an integrator. In fact, in Julia, you have integrators that do these kind of things. In Python, I'm not sure there are. But you're not going to be using the Julia integrators, okay? So you're going to have to do yourselves the time integration of this process. So the outermost loop is going to be a loop over time. Loop t until tf, which is whatever you decide for the simulation time to be. Now, what you're going to have to do is that you're going to repeat many times this process of drawing and playing the game against the pair and updating the population. We are going to take a little bit of an abstraction step now, and we are going to see that we have a fixed population size. We are going out of the limit where we consider the population size to be infinite, and therefore where it makes sense to treat x as a continuous differential equation. So you have to loop over n games, where this is the population size, okay? NH plus ND equal n, and it's fixed. So in other words, imagine that you actually have a finite population with n elements. For a time cycle to be completed, you would like, on average, to have everyone play a game, basically. Okay? So you need to draw n games. Because the idea is that everyone plays the games at the same time, okay? Because if you only play one game, and then you play another game, this means that you're not advancing time, you're just, switching your focus between different focal players. And so this would mean that you only have one pair at a time to play, but which is, of course, it doesn't make a lot of sense, because, I mean, these populations interact all together at the same time. It's not like these animals wait for the other animals to be finished with whatever they're doing before engaging against one another. Okay? So this is, if you want, why we are doing this loop. Yes?
So n, every time we end a loop, we will have another value.
We will rather?
We will have other value every time we will end the loop.
So once you finish this loop,
yes,
you advance time. And then you have another time, this other loop of n. So at each time, I don't know if is that what you were asking?
No, every time we start the loop, n will have another value.
No, n is fixed.
N
is fixed, okay? N, the population size, is fixed. Okay, this is one of the main assumptions. In fact, it's a quite important assumption to get back the replicator dynamics. If you want, we are simulating the equivalent of a Moran model, for those who know a little bit of population genetics, where each time you have some births and you replace the previous generation with the new things that are born. So this is something that is used in quantitative in mathematical models for biology a lot. This assumption of n fixed. Of course, you can have another model that doesn't make this assumption. I mean, it's totally possible to have a model where you don't constrain this, and I will tell you actually how to do it. But it doesn't go back to the equation we have been studying before. So right now you know that these algorithms that I'm giving you, on average, should give you the same results as what we have been doing the past days. If you start messing up with the ingredients, you're still going to be simulating a totally viable stochastic process. In fact, it may be even more realistic not to have n fixed, but then you don't have a null expectation for what the average should be in this in this process. Other questions? Okay. So in this loop, as probably you already understood for what I was going to, you draw the two players. So you draw player 1 and player 2. This is going to be the focal player, right? And this is going to be the opponent. With that rule, okay? And then you evaluate the payoff entry of player 1, player 2. Okay? So basically you evaluate the entry of this matrix that corresponds to this pair. Is that clear? Yes, question.
Just a quick doubt. The fixed value of n is n0 plus. What is the other n? Sorry.
No, sorry. This is just to say that it's the total population. So this is n ox plus n doves. Okay.
Oh, I see. Thank
Yeah.
you. Thank you.
Sure. Other question next to you?
One player plays with all the other population.
So this is a mean field way of doing this draw sampling process. If you want, we can say that this is mean field. Or if you want a well-mixed model in which you draw things n times, saying that you don't care if you drew the same player twice, basically. It's not a sampling, it's sampling with substitutions, which makes the whole thing easier. And on average tends to the same thing, as if you were to track the memory of who you were drawing before. So, you know, it's a simplifying assumption of how we are dealing with the model. So you say, I play this random process and time, and if I do these things in an infinite amount of times, I know that usually I draw almost everyone. I draw almost everyone. And you don't care if sometimes there is some people you don't draw and you draw someone else twice, basically. Other question?
For each game, we have a fraction of hogs. We have to define this fraction of hogs before this loop.
So, at each time point, even before you start, you have to, like in a normal physical system, you have two things. You have time, and then you have the state of the system, okay? Which is a vector. Normally it's a vector. In this case, it's actually a scalar. So you have time and the fraction of hogs at each time points, right? You will start with something, right? You will give exactly as you do when you integrate deterministic systems. You give an initial condition. Therefore, I'm going to tell you just in a moment, but this will update based on whatever we are going to do. But yes, at each time you store, you know what your state variable is. Yes. So actually, let me continue just a little bit because I think some of the doubts may clarify when you see concretely how this goes. But okay, at least these things is clear, right? You draw two players, and even though the notation is a bit heavy here, I hope it's clear what this means, right? P1, P2, it's just the matrix entry of the two players you drew, okay? And then you check if P1, P2 is bigger than 0 or it's smaller than 0, okay? Because if this is true, then P1, P2, it's gonna be a birth rate, okay? If this is false, if this is less than 0, then P1, P2, the absolute value, it's a death rate. Okay? Essentially, we are reinterpreting this payoff matrix as fitness, which is something we already did when we went from the payoff to the replicator equation, right? So you had that x dot was equal to x times 1 minus x times, let's say, pH PD minus PD, okay? Where this is fitness hoax. Therefore, if these are fitness, these are rates, okay? If this is positive, it's a birth rate. So per unit time, what is the fraction of time that you spend in a nesting site and therefore reproduce? You have a rate of rate, for instance, in this case, g half per unit time of reproduction. If this is negative, essentially this means what is your rate, how many times per unit time you're gonna die, basically, because the hoax fight so hard that they die more often than they actually manage to reproduce. So overall, it's like the birth rate, g and a half, minus c and a half, and if this is negative, it means that overall they die more than they are born. So if this is negative, this is a death rate, okay? If you want. So, and from here, these are rates that you need to couple to some stochastic process. So here goes an assumption, and the assumption is I'm going to assume that these things are Poisson processes, okay? It's an assumption. You don't have any microscopic measurement on the system that actually tells you these are actually Poisson processes, okay? You didn't measure the fluctuations of the system, so you don't know. But it's the simplest possible thing you can assume, so we are going to assume that. So let's say that these rates now I'm going to call lambda, because lambda is the rate. And therefore, is there a question? No, okay. Therefore, if you have a Poisson process with rate lambda, basically what you have is that the probability of drawing one event in delta t is equal to lambda times delta t times e to the minus lambda times delta t, okay? This is just a Poisson distribution, okay? Which will tend to lambda delta t when lambda times delta t tends to 0, okay? So this algorithm is valid only if you choose a fixed delta t, which is small enough. You cannot choose huge delta t's and hope that this will work. So from this, you know, now you need to draw if an event happened. With probability lambda or, well, whatever, pp1, p2 delta t. Okay? Do you know how to draw if something happens given a probability? Have you ever done this before? Who has never done this before? Okay. So in a computer to draw, actually you're going to have to do it also to draw players, right? To draw something with probability, okay, this is our small stochastic sampling window. So you draw, what you do is that if you have a probability P of some event, to draw if this event happens, you draw a random variable which is uniformly distributed between 0 and 1. Okay? All of your programming languages have some function that do it. So maybe I will just show you the solution just briefly to show you that line of the code, but all of your MATLAB, Python, R has things that do it for you, okay? This will this will give you a number Q which is a random variable which is the realization of this sampling process, and if Q is smaller than P, then you have the event. Okay? It's one line of code. It's like, it's nothing, you know, it's nothing overwhelming once you get the idea. Essentially, probability is always between 0 and 1. And how big it is, it tells you precisely how likely it is some event. I mean, this is precisely the meaning of a probability. Therefore, if you draw something from 0 and 1, if the probability is 1, then this something is always going to be, in fact, this is, doesn't really matter, but you could say that this is lower or equal, depending on how your thing is drawing, if it's drawing 1 or not. But I mean, this is a detail. So if the probability is 1, you're always going to draw something which is below 1, right? Because you're drawing from 0 to 1. If probability is, so this will always happen. If the probability is 0, you never draw something that is, well, okay, you may draw 0, but okay, it's a very rare situation. And so essentially this will never happen, which is what you expect from something that has probability 0. Okay? So you're going to have to do this to draw the players, because you draw H with probability X, so you need to do it. Then you do it again to draw player 2. then you do it again to draw if an event happens or not. And that now the probability is lambda delta t. Of course, lambda delta t needs to be lower than 1, okay? Lambda delta t needs to be lower than 1. In fact, choosing delta t as 1 over lambda, it's also not good, okay? It's too big, because this means that this Taylor expansion is not valid, because you have a e to the minus lambda t. This in fact, this needs to be much smaller than 1. So your lambda, your delta t should be of the order of, let's say, 0.1, the biggest lambda you expect, something like that. And absolutely it can never be above than 1 lambda delta t. That's completely forbidden. So you need to double check, please.
Well, Jacopo, I still do not get where this Poisson expansion gets in the trouble here, because we evaluate the payoff matrix in the second topic, and then if this payoff is greater than 0, it's positive, so it's a birth rate. But you say that is the lambda, and we have
now I call lambda. Now I'm calling lambda P1, P2, PP1, P2, if it's a birth rate, and or modulo P, P1, P2, if it's a death rate. I'm calling this thing lambda. Lambda is a general symbol for rates for me. Okay? So I'm just renaming it whatever is the rate, therefore the positive part of the payoff, lambda.
We evaluate the payoff matrix.
Yes.
We have a condition there. If it's
you have
a condition. If it's positive, it's a birth rate. If it's negative, it's a death rate. But where does the Poisson come in this part?
The Poisson, so these are rates, okay? And a rate is something that denotes, I mean, it depends what your model is, okay? But you have in nature things that are intrinsically stochastic. So for instance, how many times an electron jumps in an atom from one energy level to the other. That's a stochastic process. So in this case, a rate, it's actually a property of the stochastic process that tells you on average how the stochastic process will progress. But since, okay, the Poisson process is a specific stochastic process where, in fact, all of the distribution is parameterized just by the rate. So it's very convenient. It's a very simple one. So essentially, if I'm telling you that you have a certain process with a rate, it means that on average, after delta t, you will have rate times delta t events happening, on average, okay? And this is what we were doing before with this equation, okay? In this case, this equation is a deterministic system for the, therefore this equation is valid for the average. And in this case, the rate only enters the average. But in truth, these are stochastic processes. So you have like something like, now I think I can actually also use this one. Say that this is time, okay? And you have a certain rate, lambda, that determines like when events can happen. This means that in a Poisson process, you can have an event here, okay? This is an event. And then from here, a Poisson process, this is not the only stochastic process, okay? We are using Poisson processes here because, essentially because it's the simplest one, and it's also the process that determines memoryless counting events. So the Poisson process is a memoryless process, so it doesn't keep memory of what happened before. So from here you restart your clock and you can have another event, let's say here, okay? So these intervals, since the process is stochastic, are not exactly the same, okay? Then you can have another event here, another event here, another event here, okay? You can think about, I don't know, think about when you're making popcorns in your microwave and you have the popcorns that are popping. It's not that they're popping all at the same time, at the intervals of time. I mean, you have like, it's a bit random when they pop, right? They start doing ba 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 ba, then they stop, then they do pa, then you know it's not like they pop at you know fixed intervals. So the way that we do by writing down this equation as deterministic system is an approximation of a process where you are approximating the process as deterministic, whereas the actual process underlying it is stochastic. And so in a Poisson process, the average number of events in a time delta t is gonna, sorry, in time t is gonna grow as lambda times t, okay? So the rate is lambda, yes.
I'm sorry. Just to try to clarify, the event, what you're calling event, is just birth or death
Yes.
of a strategy in the population.
Yes.
Okay. And the game itself, like one strategy against the other, is just what you use to determine these rates, right?
That is correct.
Depending on the fraction of individuals and of strategies that you have trying to play with each other.
Yes.
Did this help anyone? Okay, yeah? Because I was confused. Okay, yeah. Yeah, we have to define lambda. Mm-hmm.
So lambda is defined as the modulo of whatever thing you evaluated from the payoff matrix, okay?
These PP1, P2 are the PhDs that we were calculating. I mean, no, just the pH actually, right? The line.
No. PP1, P2 are these.
These, the
yes,
entries.
the
Okay.
entries of the matrix.
Yeah. Okay, thank you.
Yes, question there.
And the
So, but before you ask your question, so I was taking a step back because I was afraid that you were confused about the stochastic process itself. So, I mean, if you are, no. Okay. Is anyone? Okay, good. So we can hide this. Please.
So, the payoff. The payoff relates only to the payoff of player one, or not?
No, you draw player one and player two, and then you take the matrix entry.
Yes. Okay.
Yeah. So player one, player two will be H, D, DH, HH. It's what you draw, okay? It's what you draw. So you will be drawing H, D into this player one, player two. So PP1, P2 is just the matrix entry, okay? Therefore, once you have it, and once you have your rate lambda, which again, it's depending on, you need to take the modulo depending on whether it's a birth or a death rate, okay? Then the probability that an event happens is lambda delta t. Okay? Because of this. because of what I told you here. Okay? And I mean, okay, you can just trust me otherwise, but it's yes, please.
I'm just still a bit confused on how the replicator equation enters this whole...
It doesn't. It's the replicator equation is the equation for the average. And what I'm claiming is that the stochastic process on average behaves as the replicator equations. In fact, I showed it to you at the end of last lab. I know I did it very fast. I probably will not do it again today. But hopefully you can trust me that this stochastic process actually on average gives the replicator equation. Okay. So once you draw if an event happens or not, it's time to update the state of the population, right? Because if events happen, then you need to change the population composition based on the events that you drew. So, and now this is the part that is a little confusing, and you need to draw if an event happens, and you have, if you look at the PDF of the handout, which I hope you all found back, all of this is written in there. It's just a bit more verbose. I mean, it's just not as, you know, stepwise as this, but it's all, the information is all there. But I think this is faster to parse than, you know, pages and pages of words. But I don't know, maybe it's not. If you draw an event, then you need to draw a third player, okay? Draw player 3, okay? And this is done so that player 3 is going to either replace or be replaced by the focal player, player 1, such that the population size is going to be fixed. And we do this precisely so that the stochastic process on average is going to be equal to the replicator equation. You can also do something else, which is you don't draw player 3, and you already take player 2 as like the one that is replaced or replaces. So if a hawk plays against a dove and dies, well, this never happens, but imagine a situation where it did happen in our model. If player 1 plays player 2 and dies, then player 1 becomes player 2. Okay, this is another option. Or you could do something different, which is that in fact if player 1 dies, you remove player 1 from the population, in which case n is not fixed anymore. I mean, you can choose any of these things. These are different stochastic processes. I mean, this is your model, okay? Model relies on some assumptions, which are most likely going to be wrong, but they might get the right behaviors of the system that you're studying, okay? And the point, though, is that these other two possibilities will not tend to the replicator equation. To have a stochastic process that on average behaves as the replicator equation, and again I showed it last time, you need to draw player 3. So you draw player 3 exactly with the same rules as before. So this is going to be a hawk with probability x and a dove with probability 1 minus x. Okay? Now, once you have player 3, you need to update the state of the population. So if you have P1 is a hawk and you have a death, If P1 is a hawk, P3 is a dove, and death, then this means that a hawk is replaced by a dove. Therefore, x becomes x minus 1 over n, okay? Yes, question there.
Yeah, just to clarify a little bit of the vocabulary, you're calling this one player 3, but it's simply the other individual in the population that you're gonna like select for the update rule that you're making.
That's correct.
That's kind of birth or death. So
Yes.
this case was death. You chose a dove to update the population, and then you killed the hawk that lost the game. Is that all of it? Yeah, and then, is that it?
So, yes, that's it. I mean, I call it player 3, even if it's not someone that plays the game, because it's the one that, I mean, it's just to make sure that it's not the same as player 2, okay? It's a new draw. It's something new that you need to draw. Okay.
Thank you.
So, and if it's a birth, if these two conditions are true, so if player 1 is a hawk and player 3 is a dove, and this is a birth, then x, this means that a hawk replaces a dove in this case, okay? Now, this doesn't happen because C is bigger than G, which is the example we were studying. This doesn't happen, but in general, in this case you have a hawk replacing a dove, therefore x is going to become x plus 1 over n, okay? And of course, okay, you do the same. I'm not going to write it down, but because it's just the complementary case. If player 1 is a dove, you do the same. And player 3 is a hawk, you do the same, okay? And remembering that x is the fraction of hawks, so in that case, if you have a birth, you have x minus 1 over n, and if you have a death, you have x plus 1 over n, okay? So this concludes the n loop. And then, after you're done with the n loop, you update time. Don't forget to update time, because otherwise your simulation will never stop. Okay? So this is it. I mean, this is the algorithm. So I think the best thing is that now you try to actually code it. There are some more information in the PDF, like the fact that you need to initialize the game and these kind of things, like, oh, now I need to switch back to that. Let's see, yes. So you're given some way to initialize the game. Maybe in the thing here, yes. Yes.
So in the end of the day, our probabilities will depend on our choice of the dt, right?
Delta t, yes. So essentially, you need to choose delta t, which is small. In this case, we tried it out, and we know, well, in fact, you know already what the maximum rates will be, because you know what your G's are. So if I remember correctly, here it told you to use 0.1 or 0.01. I don't remember. It's written somewhere. If you read the... if you read the thing. But the point is G is 10, it is going to be 10, and that's the maximum rate. Therefore, G times delta T needs to be small. So 0.01 would make sense to me. Maybe here they tried it with even 0.1, it was still fine. It's 0.01, there you go. Here. You have it. Yeah, because you need these to be valid, right? Also, this implies that the probability also is small, so that you're not going to be drawing, you're not in a situation where you would draw many events in the same delta t, in which case this algorithm breaks down. So this is an approximation. Again, I uploaded some stuff to learn the Gillespie algorithm, which is the exact way of simulating Poisson processes, but I won't have time to go through it. But you have the material in case you want to check it out. So, yeah. Yes, I'm listening to you.
There's one thing I maybe didn't fully get. The total population is fixed. I'm gonna give it a number before I start.
Yes, you will choose an n before you start. Here it's 1,000. Then you're gonna vary it as well. Okay. It's all written in the PDF.
Oh, okay. So I can just substitute its components. I can't make it bigger.
We are trying to keep it fixed so that this stochastic process on average will behave like the replicator equation. Yes. Which is why we draw player 3 and we substitute in the population. So these are actually these you have already. Actually, okay, the Python users are a little bit luckier than the others because you all have the solutions in any language, but they are in the PDFs. But there is also this notebook in the drive with actually the Python code that I wrote. Okay. So in case if you are completely lost, you can absolutely check it out. So as you see, you initialize with some initial conditions, just as you did for the deterministic case, right? And okay, here you have the extra step in which you need to specify n, and then you need to say, okay, what is the final time that I want to get to? But that you have to do also with the deterministic code. Okay, and then okay, you loop and you do these things. So just something more, since some of you never saw that. When you have to draw a player or an event, you do something like this, okay? You see it highlighted, right? So you have your probability, which in this case is just the fraction of hawks. Therefore, the probability of drawing a hawk, in this case P1, is going to be the condition of having a random number. And here you need to look up on Google, on your programming language, how you draw a random number from 0 to 1, okay? In Python, it's like this. NP is numpy, so it's numpy.random.uniform. And it draws something from 0 to 1. Less than the probability, okay? And okay, you need some way to say to the code how to look up in the matrix. If your entry for the hawk is 0, then you need to let the thing know, okay, if I drew a hawk, you need to look for the first entry in the matrix, okay? This other line of code is doing just that. You can do it in a way that is more intuitive to you. You can also have nested if statements, which are a little more verbose, but maybe a little easier to read. But you understand. I mean, if you draw a hawk, you need to look for the first row in the matrix. If you draw those, you need to look for the second. Question.
I think I have a question, but I'm sorry if it is like
That's
going
fine.
over
That's
everything. There's a probability that an event won't happen, which is when I draw a dove and a hawk.
When you draw a dove, okay. Oh shit. Yeah, okay. When you draw a dove and a hawk, it's not so. With these parameters, then the rate is 0. So for sure, nothing will happen. Yes.
Yeah, I'm talking about these parameters.
Yes.
Okay.
So that algorithm is general with respect to the model, but yes.
Yes. Yeah, I'm talking about this.
Yeah.
And then in the case that an event happens, at the moment.
So just to clarify one other thing, you always have a probability of something not happening, even if you draw other stuff. Okay. So because the probability of something happening is this. Even when you draw, say that you draw a hawk against a dove,
Okay.
you have g times delta t probability of birth, but delta t is going to be small. In fact, delta t is going to be, g times delta t is going to be 0.1. So in fact, the probability of nothing happening is 90%, okay? So this if event, if you draw an event, is going to take out most of your loop instances, in a way. The case that you were saying, in this case, no matter what delta t is, the probability of nothing happening is always 1, because the rate is 0. So, and also there are a couple of, in this algorithm, there are a couple of imprecisions and a couple of things that when coding stochastic processes one should know. I will mention them only for those that are interested in these small details, but I don't want to overwhelm you. So far you can just stick to that and it's fine. But also you should know that when you have something birth and death events, where you have a birth event and a death event, you should not draw a Poisson like we are doing. So what we are doing technically is wrong because of some very technical reasons. Meaning, if you have a birth and a death, okay, and the birth rate minus the death rate is equal to 0, drawing a Poisson with already the one minus the other will tell you that always you get 0 event. So you kill the fluctuations as well. Whereas in fact, what you should do is that you need to draw a random number of births, of Poisson births with the rate g.5, and a random number of deaths with the rate c.5. So that you actually have Poisson fluctuations also at 0. Okay? Actually, many researchers do it wrong. So, but you know, people sometimes are busy and they overlook things. Okay, so this is the first thing. I'm mentioning just in case some of you already are having experience with Poisson processes and stuff. If not, for the purpose of this lab, just do it this way. Just be aware that when you have birth and deaths happening together, you draw the birth and you draw the death, and then you take the difference. You don't take the difference of the rate and then draw the random number. The other thing is that microscopically, births are modeled by a rate. So you actually have a rate of producing offsprings. And deaths are modeled, in fact, by probability. You don't really have a rate of dying. You actually have a probability of dying in a certain amount of time. And what I mean by that is that a certain individual cannot die twice. Okay? In this sense, the correct way of drawing death is through binomial distribution, it's not through Poisson distributions. But this is a little more advanced, okay? But I just want to mention that just if in the future you start building up heavy simulations of stochastic processes, these are things you should be aware of. Especially the first thing. So this thing of Poisson versus binomial is a little bit of a nuance, because if you actually are careful about this, it doesn't really matter too much. It matters in some cases, but unless you're looking at rare events in the simulation, it doesn't matter. This, if a researcher does it, it's really bad. But people still do it. But so far you can just go ahead and do it. Actually, in our simulation, C and G are different enough that this wouldn't matter. Yes. You're done? Ah.
So I'm doing the 2D
Mm-hmm.
version.
Okay, so you did this one already.
Yes, the stochastic one.
Okay.
Yes.
Okay.
But right here in the end, so if he dies, I will replace his position because he's dead.
Right.
And right here, I will place the ID for which one to replace him. But should I put a random ID, like it could be one or the other, or it's always the opposite?
So,
for example, the hawk and dove game. If this was a hawk and dove game, if the hawk dies, it's always a dove that replaces his position, or is I just draw from random?
so the focal player is the focal player, right? And then you already drew at random the position that is going to be whatever you player three is, right? And so then you do exactly the same thing. So essentially, if you draw the same, nothing happens. If you draw the other, if this is, okay, now you're inside this if statement. In this case, is player 3 that player 1 becomes player 3.
Yeah, because he's dead. So
Right.
Okay, so
Yes.
I had to.
Yes.
So if he gives birth, he is the same. The focal player places the spot, right? the same ID?
X focal player 0, focal player 1. No. No, because right now what you're doing is you're replacing player 1 with player 2. What you need to do is that you need to replace player 1 with player 3. Right?
Play 3. But isn't this a two-player game?
It is, but you still need to draw. So you still need to draw a third component just for the replacement. It's the same thing. You did it for the stochastic one, right? So you had a third one, and you used it to replace.
Okay.
And you do the exact same thing here. Okay. And the reason it's very tricky, and it's even trickier than in this case, if you write down the equations. Actually, a colleague of mine did it, and I think they're going to publish the paper soon. If you don't do this and you use player 2 as the you introduce some correlations that actually appear in the average dynamics. So the average dynamics does not do what you expect them to do anymore. This is overall correct. I mean, this is overall what it needs to do, but the dynamics will look a little funny. Like the time evolution of the yes.
Okay.
Yeah. Okay. So I'll quickly go through the result of this, and you can continue working on it on your own. I just want to give, since I've seen that someone already got to the second one, I'd like to give you a pitch for what would be the idea behind the second problem. So essentially here what we are doing is that we are parameterizing our problem just as we were doing in the situation before, okay, with the deterministic system. We have an extra component now that is the size of the population, since now it's a finite population. And now, okay, here you're trying to cycle over initial conditions because of the specific problem that was given. But here you loop over time, as we saw, and you loop over the games. Then you draw player 1. Here it's a non-super readable way of telling the algorithm if player 1 is a hawk, is the first entry. If player 2 is a hawk, is that entry or not? Okay. So essentially, this will tell whether it's a 0, in this case is a hawk, or it's a 1, and in that case is a dove, okay? This depends on Python syntax of like a Boolean true value to be either 0 or 1, which hopefully is the same in R, but I'm not sure. You can also just say if P1 is 0, you have a hawk. If P1 is 1, you have a dove, okay? You can also have a double if statements, which is a little longer, but you can read it more easily. You do the same thing for player 2, so you draw player 2, and then you evaluate the payoff matrix for player 1, player 2, so you have what we call P, P1, P2. It's this thing here, okay? It's what's called payoff here. Now, if player 1 is a hawk, okay, and the payoff is bigger than 0, you have a birth. And whether you have a birth event or not is the same thing as you did before, but now the probability is lambda times delta t, okay? Payoff times delta t, okay? And if payoff is less than 0, then you need to take the absolute value of the payoff to get lambda, like I told you, okay? Now, you draw player 3, okay, with the same probability as before. And if player 3 is a dove, in fact, here you're drawing the probability that the replacement is a dove already, okay? And if player 3 is a dove, then x becomes x plus 1 over n, like that. Then you need to check whether that's a death, okay, same thing, but now you have x times 1 minus n, and then you need to do the case that I didn't write down, but it's like the simple, transposition of this, that if the focal player is the dove, then you also have to evaluate the payoff. If it's a birth and you're replacing a hawk, note that if you're checking whether you're replacing a hawk, you do random uniform less than x, whereas if you're checking if you're replacing the P3 is a dove, you have random uniform bigger or equal than x, meaning you're drawing an event with probability 1 minus x, okay? Question there.
I got a bit lost again. Is the first player drawn at random?
Yes.
And the second also?
Yes, it's here. The first player 1 is drawn at random.
And then there are not players like...
And this is player 3, okay? This is
Okay.
player 3.
What exactly is the player 3 doing?
It's either replacing or being replaced.
Oh, okay.
Yeah.
So the player 3 is just the result of the game? Kind of like... Because if I draw...
The player 3 is the one that it's not the result. I mean, if it's a death, it's the result. If it's a birth, actually it's the one who's dying, okay? I know it's a bit counterintuitive, but it's an algorithm, okay? It's,
No, yeah,
you draw player 3, and if it's a birth, player 1 becomes player 3. If it's a death, player 3, if it's a birth, player 3 becomes player 1. If it's a death, player 1 becomes player 3. So death is the death of player 1.
So it's just to like substitute the player 1 to continue the game?
Yes.
Okay.
Yes. And so for instance, if you're drawing a dove and you draw a hawk to be replaced, so this is a birth for a dove. Therefore, the x is going to become x minus 1 over n, because x is the fraction of hawks. So you have 1 hawks less in the population. And if you have a death of a dove, and you're drawing P3 to be a hawk, then you have x becomes 1 plus x, x plus 1 over n, sorry. So you can do it, and you can simulate the results, and basically you see that this does the same thing as the deterministic case. And then what you could do if you had more time, this actually takes a little while to run. So even if you were done with the code, you wouldn't have time to actually run this code. But what you see is that the smaller the population size, this is n equal 100, you see that you have a certain size of fluctuations. This is n equal 1000, you see that the relative size of the fluctuation is smaller. And with n equal 10,000, and the code here starts taking a little bit, I think it takes about 15 minutes to run, you see that the stochastic trajectories are very close to the average. So this is, if you want, is a numerical proof that this stochastic system, I gave you the analytical proof the other time, but this is the numerical proof that the stochastic system is equal to the deterministic one. And the reason that the fluctuation looks smaller when you plot the frequencies is something called central limit theorem in statistics, that basically tells you that when you sum many stochastic variables given certain condition that they are independent and identically distributed, you get the sum of them is going to be a Gaussian, and if you take the sum over the number of variables you're summing, which is the sample average, its standard deviation will go as 1 over square root of n. So the standard deviation of the sample mean goes to 0 as you send the sample to infinity. Okay, this is a very important feature of sampling processes. This is why you expect stochasticity in general to be more important when the population size is small, and to be less important when the population size is big. So whether you can use this equation or not depends on your population size. If the population size is small, you should use a stochastic model, not a deterministic one. Okay. So we won't actually have time to do problem number 4, but I just want to tell you what the idea is. Essentially, in problem number 4, you have a system where you have bacteria that can be close to one another in space. And what they do is that they produce some toxins. And since they produce toxins, they also produce the antitoxin. So, but some other strain will produce another toxin and the antidote for it. So if two, let's say that they are either blue or red, they are identical in the sense that there is no fitness benefit to be either one or the other. The only point is that if you are close to the other strain, you're going to die. If you're close to your kin, you're going to survive. Because you already have the antidote for yourself, basically. There is no other difference between these two strains. There is no fitness advantage. This produces a situation where you have in game you can model it with a game theory framework with these payoff matrix, which is a symmetric payoff matrix, which leads to alternative stable strategies. Either everything going to 0 or everything going to 1, meaning either all red or all blue. And in this case, what we are trying to do is we are trying to see, this is an experiment that was actually done, and they uploaded the paper on the Google Drive if you want to read it. It was published in Nature a few years ago, where they had these microbes, these bacteria that were killing one another on a petri dish, and they were tracking whether what was the spatial distribution of one strain or the other. Okay, they had some fluorescent protein produced by one of the two, and in one case it was red, in the other case it was blue. And you can model a spatial like a spatial game where you're either gonna kill or gonna be killed by someone that is spatially next to you. So you have a grid model, so you have a model, you have a situation in which this is not a well-mixed mean field model anymore. So this is a model where we explicitly have a lattice with space, okay? If you are at this position, you will interact with this, with this, with this, and with that. So you interact with the nearest neighbors, and you play the game against your nearest neighbors. So you do exactly what we did now, but instead of drawing in the whole population, you draw at random in your neighborhood, okay? And you play the game against, say, this guy. And if this guy is the other type, you may die or he may die, essentially, okay? With the same stochastic rules as the other one. And what you see is that if you simulate this system, let me actually take this up. So this was actually the experiment. So here you see oh shit. Sometimes this thing switches. So this was the experiment that they did, and you see some coarse graining. You see that the microbes like to stay together with their own kin, so that they don't kill one another. So this makes sense. And if you simulate the system, you see that, let's leave this run, no. If you simulate this system, you start from something that is very random, like this, and then progressively you have these coarse-grained patterns that form, these islands of reds and blue, okay? You see that? Which is the same as happened in the experiment. So this very simple game that you play against your neighbors can explain this pattern formation. And this is another example of spontaneous symmetry breaking that we saw in the class the other day. Because the system is absolutely invariant with respect to translational symmetry. So every position is equal to any other position, but you have the formation of like domains of strains, let's say. And if I go back to this, there are other examples of this symmetry breaking in physics, for instance, with for instance the Ising model. Okay, let's see. The legend is not here. Okay, whatever. But you can have other example of like this coarse graining. For instance, in the Ising model for ferromagnets. So like magnetism in a way like also produces situations like this close to a critical temperature. Okay, it's a little it's a lot of material. So, but just to say that you have this kind of breaking of symmetries in nature are universal across many different systems, whether be it matter physics, whether be it microbes. So, and you can use some tools from either game theory, like in this case, that you can use to simulate, or like statistical mechanics that is used to study the phase transition between different states of matters to actually study these types of phenomena in biology as well. You have all of the code. You have all of the, well, you have the solutions in the PDFs, and you have the code in the Jupyter notebook. I will upload the Jupyter notebook also for the spatial game, even though we didn't really have time to go into that. And you can, try to play around with it if you want. And I mean, I think it was good to see some stochastic simulations in this course, some concepts of stochasticity. I know that for the first time one does this, it can be quite overwhelming. Usually we start stochastic processes with tossing a coin or tossing a dice. But I don't think you came here to spend 1 hour of building a simulation of tossing a coin. I mean, that would have been a little unsatisfactory, I think. So I hope I managed to combine some quantitative biology stuff and some of the things we studied last week with some new things on how to simulate stochastic processes. I know it's a lot, but hopefully you took something out of it. All right, and we are at time. Thank you.